So today we're kind of building on what we were talking about yesterday when we learned about the Bohr model of the electron and orbitals. We're going to learn that, as with most things, it's not quite that simple, which is kind of unfortunate. The orbitals are not, remember the Bohr electron, the Bohr model was the nucleus in the middle, and then these, oops, that's not very good, but you guys get it, the distinct orbitals around the nucleus in a circle like that. This was the Bohr model of the atom. And unfortunately, like most things in science, it's not actually quite that simple. So what we get next is the quantum model of the atom. And the quantum atom model is a little bit, it's very similar in that electrons are in these orbitals, but the orbitals are not as simple as just circles around the nucleus. So, just as with the Bohr model, though, there's still distinct energy levels. So electrons still cannot go between orbitals or in between energy levels. They have to be in one of these energy levels. And the orbitals look like this here. So these would be the s orbitals, p, these are the s, this one right here is the s, and we have the p, the d, and the f orbitals. And those letters will make more sense in a couple minutes, and you don't need to know what they all look like. You just need to know that the orbitals in reality are not nice circles around the nucleus like the Bohr model suggests, but rather they are these shapes here, like the atomic model suggests. Not the atomic model, the quantum atom model. So let's write that down, the quantum atom model. Now, instead of using models to represent where the atoms are at, to represent the energy level that atoms are at, it would be really complicated if we had to draw out these orbitals and put electrons in them with pictures. So instead of doing that, to represent the energy levels that the electrons are at, we use things like this. This is called an Aufbau diagram, A-U-F-B-A-U, an Aufbau diagram. And we use this to diagram where electrons are, what energy level the electrons are in. And so electrons fill these energy levels based on a few rules, and we use these rules when we fill up electron levels. Number one is electrons fill the lowest energy level first. So if we're looking at this diagram here, we can see the lowest energy level is the 1s level, and then we go up 2s, 2p, 3s, 3p, 4s, 3d, and so on. So electrons fill the lowest energy level first. Only 2 electrons may occupy one orbital box, and they must have opposite spins. So I'll show you how to put those in. So we don't have boxes, we have lines, but the same thing. So there's 2 electrons per line there. And then subshells fill so that the number of unpaired spins is maximized. And when we go over some examples, we'll show you how you actually fill these orbitals. And so I think it's probably best just for me to do a few examples here, and then we can talk about how we're doing it, how we're filling out these electron configuration diagrams. So let's start with one of our most common atoms, carbon. Carbon, and we'll just talk about neutral atoms for now. Remember, carbon has 6 protons, and if it's neutral, that means it has 6 electrons. So let's go over to our electron configuration diagram here. And this is another way you can look at it. If you forget what order to fill the orbitals in, you can look here. You'd start at the 1s, then you'd fill the 2s orbital, then the 2p orbital, 3s, 3p, 4s, and then notice here's the tricky part. You go from the 4s orbital to the 3d orbital, and then the 4p, and then 5s, 4d, 5p. So this is the order that you fill the orbitals in, and then here you can kind of see it goes just up the next energy level, filling. So you go from 3p, 4s, and then you'd go to 4d. That's right in between 4s and 4p. So carbon, though, we're not going to have to worry about that yet. Carbon only has 6 electrons. So remember our rules here. Remember our rules. We fill the lowest energy level first, and only 2 electrons per orbital box. So here and here. And now the third rule was subshells fill so that the number of unpaired spins is maximized. So this is something electrons have different what's called spins, and you don't really need to know too much about that right now. You just need to know that they're different, and when you draw them you have one with spin up and one with spin down. So that makes sense, right? There's only 2 electrons per line, one with spin up, one with spin down. So there's 1, 2, and we're on 2s, 3, 4, and now it says subshells fill so that the number of unpaired spins is maximized. So I have 2 electrons left. I have 1, 2, 3, 4. I need 6. I go 1, 2, because I want to maximize the number of unpaired spins. So I put 1 electron in each line first, and then if I had more, I would go back and start to double them up. So first you leave them unpaired, and then if you have enough electrons, then you go back and start to double them up. So, but we don't. This is just carbon. We just have 6, and so this is the electron configuration diagram for carbon. Now if you notice, if you look at this periodic table, you might say, why is it that 3D comes in between 4s and 4p? Well, we can kind of look here. You see 1s, and if it's easier, you can think about this is helium, helium coming over here. We have 1s, and then 2s, then we go over to 2p, and 3s, 3p, and then 4s, and this is 3d. We call this 3d, and then 4p, and then down to 5s, 4d, 5p, 6, and then on down. So the last thing we would do to finish this up, instead of drawing out this whole chart, to easily communicate the electron configuration of any atom, we write it like this. We write 1s, 2, 2s2, you can probably guess 2p2. So 1s, this is the orbital, right? That's the name of the orbital, 1s, and then the superscript is not squared. This is not squared. We say 2. It's the number of electrons that's in that orbital. So the 1s orbital, 1, 2, 1, 2 electrons. The 2s orbital, 1, 2 electrons. The 2p orbital, here we can have up to 6, but right now we only have 2. So this is how you would write out the electron configuration for carbon. Okay, let's do a little bit trickier one now. Let's try nickel. Nickel. If you don't have your periodic table handy, we know that nickel has 28 protons, and let's say it's electrically neutral, so that means we have 28 electrons. Now normally I would get a new diagram and restart and everything, but since we'll just continue on with this one. So we need 28, so we'd start the same way we did with carbon. 1, 2, 3, 4, 5, 6, here's 7, and now they're all unpaired. Now we have to start going back and pairing them up. So there's 8, 9, 10, now I go to 4s, 11, 12, 14, or 13, 14, 15, so now they're all unpaired. Now I go back and start doubling. 16, 17, 18, 19, 20. Now I'm 3D, 4s to 3D, remember. 21, 22, 23, 24, 25, so they're all unpaired first in the 3D orbital. Now I go back and start pairing. 26, 27, 28. And there we go. I think I counted that right. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4, 6, 8. Yes, okay, good. I counted correctly. And it's always a good idea when you're doing an element with a lot of electrons to go back and count and make sure you have the same number of arrows that you have electrons, just to double check your work, because it's easy to miscount when you're writing in all these arrows. So there's my electron configuration diagram for nickel. Now if I want to write it shorthand like this, you just start at the bottom and write out the orbitals. So 1s, I have 2 electrons in that orbital. Then I go to 2s, there's 2 electrons. Now I'm on 2p, and there's 6 electrons in that orbital. And 3s, 2 electrons, 3p, 2p6, now 4s, 4s2, and now remember 3d. So 3D can have a maximum of 10, right? Because there's 5 boxes here, and each box could have 2 electrons. You could have a maximum of 10. We don't. We have 2, 4, 6, and then 8. So 3D 8. And there would be our electron configuration for nickel. Okay, so the last example I want to do is going to be an ion. Sometimes you get ions, right? So let's do magnesium 2+. Magnesium's atomic number is 12, so it has 12 protons. And yes, you'll notice that this diagram just appeared because I paused the recording and I copied and pasted another one. So magnesium has 12 protons, and if it was neutral, it would have 12 electrons, right? So if it was neutral, it would have 12 electrons. This is +2, and that means that we could go through all this if you wanted to. Remember, we learned how to calculate how many electrons an ion has. But if it's +2, that means it must have lost 2 electrons. So it did have 12. It lost 2 of them. Now it has 10 electrons. So we only have 10 electrons here. So let's do our diagram. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we would be done. So the ion, +2, right? +2, 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're done. If it was neutral, if it was 12 electrons, then we'd go to this shell here, and we would go, so okay, there and there. But it's not, right? If it's an ion, we would not do that. It lost those electrons. Those electrons went away. Now notice it lost the electrons from the highest energy level. That's important to note, right? When an atom loses electrons, they're lost from the highest energy level. So if you wrote out magnesium and you had those 2 in there, and then you said, oh, it's actually an ion, it lost 2 electrons, it would not lose the ion, it would not lose the electrons from the 1s or the 2s or the 2p orbitals. It would lose them from the outermost orbital, the one with the highest energy, which would be the 3s orbital. So those are the 2 electrons that go away, the ones with the most energy. And then we're left with this, and so we could write out our electron configuration: 1s2, 2s2, 2p6. And there's our electron configuration for magnesium 2+. And then also important to remember, if we had an anion, an atom with a negative charge, then we would obviously be gaining electrons. You'd have to add electrons to your diagram, still following the same rules, making sure you're adding them unpaired first and then pairing them up and going up through your energy levels, just like we see on this diagram here. Alright, I know that's a lot, and this is kind of a difficult topic, so if you need to, watch this a couple times, but that's the gist of it. And once you do a few, it's really not that hard, and it's kind of fun to fill in the arrows and then write out the electron configurations.